In this video, we'll talk about solving linear inequalities in one variable, including understanding set builder notation and interval notation. So let's start with the definition of a linear inequality in one variable. Let's review some inequality symbols. So there are four basic inequality symbols that we'll be seeing. The first one, the symbol, when you see that, you would read it as is less than. Below, the symbol just turned in the opposite direction reads is greater than. And then if you put the line underneath, that includes an equals. So the first symbol you see on the right is less than or equal to, and then is greater than or equal to. So a linear inequality in one variable uses one of these four inequality symbols. The remaining format of the statement is much like the linear equations that we looked at last time. So your definition reads, a mathematical statement of the form ax plus b is less than 0. Do note that that less than is less than could be any four of these inequality symbols, where a and b are real numbers, a is not equal to 0, and again that less than symbol can be replaced by any inequality symbol. So we're going to look at how to solve these linear inequalities a little bit later on, but first we're going to talk about the solutions and how to represent the solutions. I want you to recall that a solution is a value of a variable that makes a statement true. So in this case, the statement will not be an equality statement, it'll be some sort of inequality statement. But we can test to see if that kind of statement is true by just determining whether it makes sense mathematically. So let's look at the example. X is greater than or equal to -4. And let's just look at any solution, any possible value that we can plug in for x that would make that statement true. So here I have it written here. So when I'm thinking about a solution, I want to think about a number that I can replace with x to get a true statement. So let's say that x is replaced with 5. 5 is greater than or equal to -4. Now that is true. 5 is to the right of -4 on the number line, so 5 is greater than -4, and I need to satisfy either the greater than or the equal to. So this would be true. I could think about maybe 0 is greater than -4. 0 is also bigger than -4, so that is true. And I could have, since I have the equality, -4 would be a solution to that statement, because if I say -4 is greater than or equal to -4, since they are in fact equal, that is true. So that we see that there are lots of values, or at least 3 so far, that make this statement true, and in fact that there are more as well. It's also important to maybe think about some of the values that don't work, just so you can understand how to determine whether or not an inequality is true or false. So let's say I replaced x with -6 instead. -6 is greater than or equal to -4. Well, comparing -6 and -4 on a number line, -6 falls to the left of -4. So that means that -6 is not greater than -4, it's less than, and these two are not equal to. So since neither of the conditions are met, this would be a false statement. Now, since we have that kind of picture drawn there of the number line, we might want to think in general about values that would make this statement true. So I'm just going to think about a number line for a second. I'm just going to place -4 on this number line. I'm just going to put it right in the center for a second. I want the values that are equal to -4, but are also greater than -4. So I could take any of those values if it's equal to -4 or if it's greater than. Now I know that the values that are to the right of -4 will make this statement true. So I'm going to kind of shade those in here in green. So all of the values on the right of -4, and this would go out, my shading would go out to positive infinity, would keep going. All of those values are values that would make that statement true. And I want to make sure that I am showing that I am including -4 as well. We're going to talk about ways to graph in just a moment, but one way you might have seen so far is a circle that's shaded in a closed circle. So that's showing that -4 is included in this solution set. So solution set is just the collection of all possible values of the variable that make a statement true. And as we've seen that in that picture, we're shading in really an infinite set of values. So we're going to talk about different ways to represent a solution set throughout this section. So there are really 4 general ways. The first way we kind of already been working with, it's kind of an informal written description, either using words or symbols. So just like an equal sign or an inequality symbol on its own, or maybe writing it out in words, would be one way that we can describe a solution set. Often graphing is helpful when we're looking at solution sets that have many different values, especially if we have infinite values. And then we have this very formal way called set builder notation. And then we have a little less formal, but or I shouldn't say less formal, a little less symbol heavy way of writing called interval notation, kind of like a short hand way of writing a set, a chunk of the number line. So we're going to start with set builder notation. Set builder notation is just a very fancy way of writing a statement. So we're going to see in this section, since we're working with inequalities, that those inequalities are going to be used in our set builder notation. So let's say, for example, we have the inequality x is less than 6. So one way that we could write that solution set in set builder notation, or we do have a set here, so we're using our set notation brackets. The first thing we need to do is describe the variable. So whatever variable is being used in that statement is the variable that is going to begin our set description. So following that, the naming of that variable, we have a vertical line, and then we have a description of what that variable is, or what part of the numbers it can represent. So in this algebra course, at the moment, we're focusing on real numbers. So our solutions will be elements of the real numbers. So we're always going to begin our set builder notation with that statement that we're starting with the set of real numbers, and then we're going to focus in on only some of those real numbers. Remember, real numbers are just numbers that are found on the number line. So this first statement, x is an element of, so this symbol means element of in set notation, the real numbers. So that's really generally always going to be there. And then following, you'll have some sort of description, generally using an inequality. So in this case, our inequality just tells us that x has to be anything less than 6. X is less than 6. So we would read this statement as the set of all x such that x is a real number less than 6. But we would write the set builder notation in this form. In the second example, we have an inequality that is not yet solved, so we haven't yet isolated the y. We're going to talk about how to solve in general, but if we want to just kind of think about this statement for a second, y plus 1 has to be greater than or equal to 0. So if we were to solve this for y, isolate the y by subtracting 1 from both sides, we would have y is greater than or equal to -1. So any value of y that we plug in that is bigger than or equal to -1 would make this statement true. One way that we can write that formally is using the set builder notation. The set of all y, again because the variable is y, such that, the vertical line, y is an element of the reals, y is greater than or equal to -1. And again, the way that you would read that is written in words down below as well. All right, next we have graphing and interval notation. So when we have an inequality, it's often helpful for us to graph that inequality. these two slides, this slide and the next, will show you a way to go from an inequality to a graph to an interval notation. Interval notation is kind of best understood looking at the graph. So in this first case, we have x is less than or equal to a. So the graph shows the shading, so the left of a, whatever a happens to be. One way that we could represent equality is by using this square bracket, putting a bracket at that location. That's another way instead of the closed circle to show that we're including. So interval notation kind of describes the section of the number line that's being shaded. It uses the smallest value in the shading and then the largest value in the shading. Now in this case, the shading goes on forever and ever. So we say that it goes as small as negative infinity, and that's the symbol that you see here, an infinity symbol with a negative in front of it. Since negative infinity is not a number, but an idea that something continues to go in that direction, we use parentheses around it. Parentheses are a way for us to show that a number is not included. And again, infinity is not a number itself, so we can't actually include it. Now, a is the largest possible number in this set, and it is included, so we would list that a after a comma and put the bracket around it. If we compare this to the next example, x is greater than b, we are looking at a strict inequality. We're not including b, and we're happening to go in the opposite direction. So the shading gets larger than b to the right of b, goes on to positive infinity, but we're not including b, so we're using parentheses there. The interval would be parentheses b, comma, infinity, parentheses. Again, the parentheses around the b are used because b is not included. Parentheses are always used around infinity. And the order is important, so b is smaller than infinity in this case. We will also look at compound inequalities next. Compound inequalities have often two bounds, and these are three examples of that. So we could have an inequality where we have a lower bound and an upper bound. If those two bounds are included, we call this a closed interval. So this means that x is between a and b, but can be equal to a and b. And if you take a look at the graph, we're shading everything between a and b and including both endpoints. So the interval notation would come right from that graph. Take the smallest number, comma the largest. Since they're both included, we're using brackets. We could have an open interval where both endpoints are not included, but we're including everything in between. So again, if you compare this picture to the last, the only difference is that a and b are not included, so there are parentheses at the end of each of those shaded, that shaded region. The interval a comma b, but with parentheses on both sides to show that we're not including the endpoints. And then you could have a half open, half closed interval where one side is included but the other is not. In this case, I have an example where the larger value is included at b, but the lower value at a is not included. However, we are including all the values in between. So here, x can be anything between a and b, and equal to b, but not equal to a. Notice the interval, a to b, a comma b, parentheses, bracket around b. It's important to remember the following when you're talking about interval notation. The two values in the interval go from least to greatest. So always 2, the smaller one first, the larger one second. If you have less than or equal to or greater than or equal to, you're using brackets. If you have less than or greater than or positive or negative infinity, you're using parentheses. In the next video, we'll look at examples of solving linear inequalities and we'll work with interval notation.